Hello once again. So I hope you have watched part 1. So this is the part 2 of the phenol series, and now we have just started the preparation, and we are going to prepare phenol from salicylic acid. So it is very easy to prepare phenol from salicylic acid. We can see that there is one COH group in salicylic acid. So if we can remove the COH group, then we will get phenol. So I hope you can recall that there is a method by which we used to convert benzoic acid to benzene, or for instance any acid into an alkane with a loss in one carbon atom. Right? So this process was known as decarboxylation because the CO2 gas was always evolved in these type of reactions. So here also similar phenomenon is going to take place. So the COH group should be removed right now. And how shall we accomplish that? So the reagent is soda lime. So sodium hydroxide plus calcium oxide together they are known as soda lime. And then we have to heat it. So a shortcut is that whenever we see soda lime and heat, it means that there will always going to be evolution of CO2 gas, right? It always implies decarboxylation. Wherever NaOH and CO are written and then heat is written, it always means decarboxylation. So here we see that decarboxylation will take place. So this CO2 gas, this will get evolved and we will get phenol and CO2 evolved. So this was how we prepare this is how we convert salicylic acid to phenol. Now the next method is from chlorobenzene. So this is chlorobenzene. So we know that alkyl halides they react with NaOH or KOH, any alkali, to form alcohols. This is chlorine, mind you, alcohols plus NaCl. It can be any halogen. We have taken chlorine over here. So phenol can also undergo same reactions like this. RCl, just R will be benzene over here. Chlorobenzene plus NaOH or KOH, any alkali, will give alcohol plus NaCl. Alcohol here is the phenol. But there is one problem over here, that how haloarenes differ from haloalkanes in these type of reactions. And yeah, there is one difficulty, that is we know that chlorine has a lone pair. So this chlorine lone pair will resonate with the benzene ring, and as a result of that, a partial double bond character will be developed between the carbon chlorine bond in any haloarene. So, due to this partial double bond, we know that partial double bonds are always more stable as compared to normal single bonds. So, due to this partial double bond, the stability of this carbon chlorine bond will be more. And we all know that more the stability, less is the reactivity. So, the reactivity of haloarenes towards these reactions with alkalis are very less. So, as a result of that, we need to use drastic conditions, high temperature, high pressure. In only these drastic conditions or vigorous conditions, the cleavage of the CCl partial double bonds will be taking place, and we will get the corresponding phenoxide, and then we need to hydrolyze that phenoxide so that it is converted into phenol. So let's see how that happens. So first we treat it with NaOH, just like we treated any alkane or haloarine with NaOH. So chlorobenzene is also treated with NaOH, but there should be high temperature and high pressure. So we have taken 623 Kelvin, which is quite a high temperature, and 300 atmosphere pressure. So these are drastic conditions or vigorous conditions. Otherwise, the cleavage of the CCl bond won't be taking place in haloarenes. So we have used drastic conditions. So what we get is sodium phenoxide. Now sodium phenoxide. Why sodium phenoxide form? Why not phenol directly? Because if phenol is formed, there is NaOH in the medium. And just as I have shown you in the last video, that phenol reacts with NaOH to form phenoxide, sodium phenoxide, and water. So the phenol formed will immediately react with sodium hydroxide and it will form sodium phenoxide. In order to avoid this, we need to give H plus or dilute acid or hydrolyze it. So complete pure yield of phenol will be obtained. So we hydrolyze it with H plus, we get phenol. And this reaction has a name. This is known as Dow's process. Dow's process. So Dow's process is the method to prepare phenol from haloarine, specifically chlorobenzene. We move on to the third reaction, the method of preparation, and that is from benzene diazonium chloride. So we all know the structure of benzene diazonium chloride. N triple bond N plus Cl minus, or we can write it like this, N2 Cl plus minus. So let's see how benzene diazonium chloride is prepared first, and then we will show how it can be converted to phenol. So I'm drawing a flow chart over here. This is benzene. So benzene can be converted into nitrobenzene. And how will we accomplish that? We will add concentrated H2SO4 plus concentrated nitric acid, right? This is a nitrating mixture, also written as NM. Nitrating mixture treated with benzene will give nitrobenzene. Now, this to convert this NO2 to NH2, that is aniline, we require reduction. So, tin plus HCl or iron plus HCl, any metal plus acid, it will always liberate hydrogen gas, and that hydrogen gas will be helping us to reduce this particular NO2 group to NH2 group. So the product that we are getting is aniline or aminobenzene. Now this aniline needs to be converted to benzene diazonium chloride. And how do we do that? So we treat it with NaNO2 plus dilute HCl at a very specific temperature, 0 degree to 5 degrees Celsius. And why is that so? Actually, the acid that we need to prepare benzene diazonium chloride is HNO2. Okay? But HNO2 is a very unstable compound. It will decompose very easily during the reaction. And we don't want that, we want to avoid that. So we have to prepare that particular acid, that is HNO2, in situ, means on site, on the site of the reaction, instantaneously, because the moment it is formed it is going to decompose. So in order to avoid that, we have to prepare it at the time of the reaction on site or in situ. So that is why we react NaNO2 plus dilute HCl. These two together will form HNO2 and they will form benzene diazonium chloride. Now this 0 to 5 degrees Celsius is a very important range of temperature, and that is because at temperatures higher than 5 degrees Celsius, this is a very unstable compound. Okay, so at higher temperatures greater than 5 degrees Celsius, this will decompose. All right, it can give phenol, can give other compounds. So like this, it will decompose, and this is a very good leaving group because positive charge on nitrogen is obviously unstable. So this can easily liberate nitrogen gas, right? Nitrogen gas is a stable product, so it can easily liberate nitrogen gas at higher temperatures than 5 degrees Celsius. So the temperature has to be strictly maintained between 0 degree and 5 degrees Celsius. If you ever do the practical, you will know that we generally use an ice bath a kind of an apparatus to prepare this benzene diazonium chloride. So this temperature from 0 to 5 degrees Celsius has to be maintained because at temperature higher than 5 degrees Celsius, this can decompose. That means this nitrogen gas can leave because this is a very good leaving group, and so yeah, this temperature is very important. We always have to write this temperature with this reaction. Now, if we warm this benzene diazonium chloride with water, we will get phenol immediately because, as I said,